The first circuit configuration that we're going to look at in more detail is our buck converter. And so as we talked about in our overview video, our buck converter is going to be reducing our input voltage, which we're typically going to call our V raw. And so it's going to reduce that to a lower level via some variable duty cycle. So we're going to have some control over our switch, and by adjusting how often that switch is closed during a particular period, we can adjust how much we reduce this by. Okay, so let's talk about a variable here before we look at our diagram or our circuit. And so for our buck converter, we're going to have this D buck, which is our duty cycle ratio for our buck converter. And so this is going to be defined as our on time for our switch over the period for our switching cycle. And so again, this is our duty cycle ratio. And so notice that this definition of D buck does not include a TS on, like we saw in a previous definition for a similar duty cycle. And that's because, remember, we're assuming that our switching occurs instantaneously, so that TS on is just going to be 0. So I'm going to be calling back to these assumptions as they come up. And so what we're going to see is that ideally our output voltage, V out, is going to be equal to the input voltage, V raw, times this D buck variable. And so we're going to come back and we're going to prove that here in a little bit. And we're also going to have that our output current, I naught, is going to be I raw times 1 over D buck. And so like we've talked about previously, that's just from conservation of energy. So we're assuming we have a lossless circuit, so we're going to have the same power in as we have out, or the same energy in as we have coming out. Okay, so let's take a closer look at our circuit configuration for our basic buck converter. So here we have our configuration, and I've left a few things unlabeled so we can kind of talk through it. So on our input side over here on the left, we're going to have our input voltage V raw. And so we see that our V raw is either connected or disconnected from the circuit based on the position of this switch up here. So into this switch over here, sort of on the left, we have our input current, which we're going to call I raw. Sort of on the other end of our circuit is our output. So over here we have our output voltage V out and our output current I out. And notice we also have this capacitor here, and this is related to one of our assumptions that we mentioned in a previous video. We said we assume we have this capacitor, which is helping keep this output voltage relatively constant. So it's just helping maintain that V out when our V raw is not being applied. And so the key components here are our inductor and our diode L and D respectively. So in order to help our analysis, which we're only going to do qualitatively at first, we can label a voltage across this inductor of VL, and we can label a current through this inductor IL. And so the basic process here is we can see that when the switch is closed, we're going to have current flowing through the inductor. Our inductor is going to be charging up. Remember, for an inductor, so our current is always continuous. So current continuous in an inductor. And so if you forget that, an easy way to remember is to think about our inductor IV equation. So we have that our inductor voltage is equal to L di dt. And so looking at this di dt, we notice that an instantaneous change in current would make that di dt infinity because we have dt equals 0. And so basically an instantaneous change in current requires an infinite value of voltage, which just isn't physically possible. So we have this current slowly increasing as it's connected to V raw, it's charging up. Then we disconnect V raw, and there's still some energy in that inductor. So the switch is opened, but we still have energy in the inductor. The diode is preventing current from flowing sort of backwards through the circuit, so our current is still being discharged through our load, and again our capacitor is sort of keeping that voltage across our load constant. So let's look at some waveforms of some of these key values and see if we can get a better look at what's going on. So I've got several plots here that we're going to fill in. So we have our switch state, our voltage across our inductor, and our I raw, and then finally our I naught. And so I'm actually going to need to adjust our voltage here because we're going to have some negative values. So let's just bring this up to here. And so like we've seen with similar videos, I'm trying to plot these so that our times are all lining up. So they're all plotted one right on top of the other, so the times are going to line up in these various plots. So let's first look at our switch. So our switch is going to have sort of two states. So our switch can be on, or down here we'll say this is off. So on, of course, being closed, so our current is flowing through the circuit, and then off is open. So on, and then I'll just put in parentheses under here, closed. And so let's say that we have, let's do this in blue. So let's say we have our switch is open for some amount of time, and then after some amount of time it closes. So we say our switch is on, and it stays in that state for a little while, and then it goes back to being open, and then it stays open for a while, and then at some time it closes again. So of course we just have one of two possible states here. It's either going to be open or closed. And so we can use this information to help us define our duty cycle. So this time that our switch is closed is going to be our T on, whereas this time here between sort of where we start our T on and our next T on is going to be our overall period T. So our T on over that T is going to define our duty cycle. So we see that up here is our D buck. Okay, and so of course by adjusting that duty cycle, if we look at this equation, we can see by adjusting that duty cycle, we're able to adjust the relation between our output and input voltages. And we'll come back and look at that in a little bit. Okay, so that's our switch. So that's pretty straightforward to see. So now how about our VL? So we can figure out our VL by doing a simple KVL loop. So our KVL loop is going to change a little bit depending on whether our switch is open or closed. So when our switch is off, so in the open position as it's drawn here, we're not really including anything to the left there. So really we're just going to have something like this. And so one thing to note is that we're assuming we have no losses in our coil, so in our inductor, our switch, or our diode. So let me just come over here and make a note that we're neglecting inductor, diode, and switch losses. So we're assuming all of these components are ideal. And so for our diode, that means we're assuming we don't have any voltage drop across it. It's just off. It's not allowing current to flow if it's trying to go downward, and it's allowing current to flow if it's going upward with no resistance, essentially. So with that being said, we can see for this open switch case, our inductor voltage is just going to be equal to negative output voltage. So we're going to have one value down here that's going to be negative V out. Now, if our switch was closed, so if our switch comes down to this position here, so this would be closed, parentheses on. So now what our KVL loop is going to look like is we need to include this V raw. So now our V raw, we're going this way, and we see that our VL is equal to V raw minus V out. So let's come and add that on our plot here. So we have V raw minus V out. And although our inductor current cannot change instantaneously, our inductor voltage can change instantaneously. And so that's actually what we see happening here. So we're going to be at one of these two levels. So when our switch is off, or in the open state, we're going to be at negative V out. And then as soon as our switch turns on, we're coming up here to V raw minus V out. And then we're staying up here as long as the switch is closed, and then we're switching back down. And so these should be instantaneous jumps lining up with our switching states up above. So we have something that looks like this for our inductor voltage. But now what we're really interested in is this output current. And so for our output current, it's going to be useful to first look at our I raw, and then we can relate that to how that affects our inductor current and ultimately our I out, because we're going to assume that we don't have any current flowing down through this capacitor, of course, because we're going to assume that our circuit is in steady state. So another assumption here is for these plots, we're assuming our circuit is in steady state. Okay, and so that doesn't mean DC steady state, that doesn't mean our inductor is behaving like a short and our capacitor like an open, but rather we've already passed through the initial charging cycle, if that makes sense. So obviously at some point we're going to have to close the switch for the first time, and for that very first time our inductor charging cycle is going to look different than it will in subsequent cycles. So we're saying we're already well into the operation, it's been opening and closing for a while, and we're just kind of coming in the middle here. Okay, so let's talk then about our I raw. So if our switch is in this open state, and so let me just come up here and put open. So if our switch is in this open state, which is also we're calling off, of course our I raw is going to be 0 because there's nowhere for this current to flow. So let's say this is 0 here while our switch is open. And we'll say that it's going to ultimately be going up to some value I2. Well, actually we're going to see this is related. We're going to have an I1 and an I2 value. So what's going to happen is, again, our inductor current cannot change instantaneously. So we know that if this inductor has already been charged up, the switch closes, it has some current in it, the switch opens, and that current is going to be dropping. We're going to be dissipating energy to our load. So we can think of having sort of a load resistor over in this area as our simplest case. So our inductor current is decaying away as we're supplying power to that load. So then our switch closes again, and now we're charging our current back up. But remember, our current in the inductor has to stay continuous. So it basically has an upper and lower limit. The lower limit is right before the switch closes again to start charging it, and the upper limit is sort of right before the switch opens again. It's been charging for a long time. So what that's going to look like in terms of our I raw, and so note our I raw is not equal to our inductor current, but our I raw is going to be 0, and when that switch opens, when the switch closes, when it becomes on, what's going to happen is we're going to be at that lowest current level because the inductor has been discharging through the resistor, so it's been losing energy. Now over time, as we're charging that inductor up, the current is slowly going to be increasing until we reach our current level I2. And then once our switch opens again, the I raw is going to go back to 0. And it's going to remain at 0 until the switch closes again. And then it jumps back up to whatever our lower level of our current is, the I1. And then it's going to slowly begin charging up towards I2 again. So we get something that looks like that. And just for clarity, let me make some dashed lines. So this level here is I1, and this level here should be I2. So I've kind of missed that a little bit. And this here is also I1. Okay, so that's what our I raw looks like. So now how does that translate to our I out, which in this case, our I out we're assuming is equal to our IL because we're assuming we have 0 current going through that capacitor. Well, so what that's going to look like is essentially just alternating between I2 and I1. So these are the same I2 and I1 that we have in the plot above for I raw. But again, note that we're coming in sort of in the middle. This switch has been opening and closing for a long time, so we're saying it's in steady state. We've passed that initial charging period. So I'm just kind of drawing out my I1 and I2 to help in my drawing here. So the switch has been closed for a while, and then it opens. So in this initial case, it's open, so we're sort of decaying a little bit here. But then we reach to this point where our switch closes again. So now we're charging up and we're following I raw, because when the switch is closed, we see that these 3 currents labeled along the top are all equal. It's just when that switch opens, of course, they're not equal to one another. But then our switch opens again. So when our switch opens again, this inductor is then discharging through our load, and we decay to a lower level of our current I1 until our switch closes, and then we're charging back up towards I2. So we see we sort of have this, not necessarily a constant current, but based on our design, we can make this ripple effect in our current smaller depending on our need. So this is the basic operation of our buck converter in terms of our plot. So now let's look at how we can describe that with some equations. So if we're talking about a single period, we can talk about the input power and the output power. So for single period, which we defined above as being T, we have power absorbed and so this is power absorbed, maybe let me be more specific, by the circuit. What we have is our UN is equal to, and so really, so I'm recognizing this in my notes now, but this should probably be energy, and I'm not sure if I just have a typo or if maybe there was one in the book, but we're talking about energy absorbed because we have power times time. So our energy in, though, is going to be T on, so how often that switch is closed, times our V raw, so we're looking at the input side, and then for our V raw, during that input time, so if we look during this input time, so we're talking about T on, so we have V raw on our input, and then our current, we can do the average of I1 and I2. So let's come down here and do that. So that's going to be I1 plus I2 divided by 2. So that's just going to be T on V raw, and we notice that that's the same as our output current. So in this region, our I raw is actually the same as our output current. So we can just simplify that and say that that's I out, like that. Okay, so now if we consider the same period, we can look at the energy that the circuit is delivering to the load. So energy circuit delivers to load. And one thing to note too is keep in mind that we're assuming that the circuit is lossless. So we're assuming only ideal components, and I think that might not actually come in until here in a second, but we'll go ahead and put it down here. So our output energy then is going to be the period T times V out and I out, where we can think of V out and I out are sort of our average voltage and our average current over time, and of course we multiply that by our whole period T. So then what we can say is we want to consider our conservation of energy. So our conservation of energy here is where we're noting that our circuit is lossless. So we're saying we're not losing any energy in the inductor, in the diode, in the capacitor. Of course, that's not actually the case, but it's going to be a good approximation. So what we then do is we're equating our input energy to our output energy. So we're saying none of it got lost in the circuit. So we're saying UN equals U out. So we're just going to substitute those two equations in. So we had T on V raw I out for our input energy, and then for our output energy we had our period T, V out, I out. And so we can see, of course, that our I out is going to be canceling, and then let's rearrange this equation. We can solve for our V out. So we can say our V out is V raw times our T on divided by T. Well, we had previously defined that T on over T to be our D buck, so we can say V out equals V raw times D buck. And so basically what this shows us is that we had already written this equation before, but now we've sort of proved it. So if we're assuming a lossless circuit, then we can set our output voltage just by choosing the duty cycle for that switching waveform. One thing to note, based on this definition of our D buck being T on over T, our dbuck is always going to be less than 1. So dbuck always less than 1. And so as advertised with our buck converter, what that means is that we're going to be decreasing voltage. And so that's independent of any of those component values, our inductor, our capacitor, our frequency, anything like that. So this is, for a buck converter, always going to be less than 1. So one other topic we want to talk about in this video really quickly is calculating our ripple current and ripple voltage for our buck converter. So we kind of saw, we didn't plot our output voltage explicitly, but we kind of saw, we're assuming that our output voltage is held relatively constant by that capacitor. But for our output current, we saw that sort of ripple. We saw it's not a constant I, it's actually going up and down between I1 and I2. So we want a way to calculate that ripple current. So what we can say is, so let's note here, we're looking at ripple current first. So our ripple current, we can call this delta I buck, and we can say that's equal to I2 minus I1. So that's sort of how much ripple we have in that output current. Well, let's go back to our inductor IV equation. So we say for our inductor, V equals L di dt. And so we can rearrange that, and we can say di is equal to V divided by L times dt. And so our di, so we can write that in a little different way. We can say instead of di, well, let's just call that a delta I. And so since we're talking about I buck, or I out, we can call that delta I buck. So now we also have for our dt, so what is our change in time while we have that change in our I? So let's come back up here to our plots. So we're saying in this time frame where we're changing between I1 and I2, what's our time? Well, that's just our T on. So that delta I buck corresponds to a dt of T on. So we have T on, and then we have our V over L, and our V for the inductor is going to be V raw minus V naught. And so again, let's come back up to our plots, and we're just saying that during this time, our inductor voltage is this V raw minus V naught. So we're dividing that then by our inductance. So now we can sort of play around with this equation a little bit. Using our definition of d buck, we can change this T on to be T times d buck, so that's our period times our duty cycle ratio. And now we're multiplying this by V raw minus V raw times d buck. So I'm using the relationship between our output voltage and our V raw and d buck to substitute there, and we can divide that by L. And so I'm just kind of playing some games to simplify this a little bit. So then rearranging some of those terms, we can simplify this and say that our delta I buck, which is our ripple current, is equal to, so we're going to have V raw times d buck divided by frequency. So that's our switching frequency, so that's basically just comes from 1 over T here, times the inductance, and then all of that is multiplied by 1 minus d buck. So that would be how we could calculate our ripple current based on our raw input voltage, our duty cycle ratio, our frequency, and then we see it also does depend on the value of our inductance. One other thing that we're not going to go into details deriving, but we can look at what our ripple voltage is for a constant load. And so remember, ideally we're assuming that we have a constant V out, but in practice that's not necessarily going to be the case. So we're going to say it can be shown for a constant current load. So our load is drawing a constant current, that our delta V buck, is equal to V raw times d buck times 1 minus d buck divided by 8c f squared L. And so we can think back to that assumption we stated in a previous video. We said we're assuming our capacitance is such that the voltage is constant. And so what that means is that we would ideally have an infinite capacitance. So we have a capacitance so large that the voltage just isn't changing. And so we can see from this equation that holds as well. So if that C in the denominator is infinity, of course our delta V buck is going to be 0.